So I'm one of the faculty in mechanical engineering at UH, and my main area of research is in robotics, and more specifically, we call ourselves human-robot interaction. And the system that I'm going to tell you about today is our robotic surgery system. So the question you should be asking is, what's the point of robotic surgery? Why do you want to do surgery with a robot? And the explanation is a little bit involved, but basically when you think of surgery, 20 years ago, if you needed to have your gallbladder taken out, your appendix taken out, something along that nature, they basically opened you up and reached in and fixed what needs to be fixed and closed you up again. And that was fairly straightforward as far as a surgical procedure, but it's terrible for the patient because you have a big scar and it takes a long time to recover from this, and there's various risks involved, infection, complications, you're occupying a hospital bed for a couple of weeks and they'd rather send you home with somebody else in there. So the first big change was a switch to minimally invasive surgery from open surgery. So instead of having one great big scar, there'd be a number of small incisions. And then everything's done through these very small incisions. So the first thing that has to go in is a camera on a stick, endoscope camera. This goes in first, very small incision, typically in the navel. So the surgeon can see what's inside first of all, and then the rest of the incisions that go in are for long, thin instruments to do the actual surgery. This is much, much better for the patient. The incisions are very small. Recovery is typically the next day or even the same day. However, it's much, much more difficult for the surgeons. These long, thin instruments are pretty awkward, pretty tiring. It's very disorienting. Everything has to go through a single pivot point of that insertion point. So things are flipped around. You move your hand up and then the tip of the instrument goes down. So there's quite a lot of mental gymnastics involved in doing this manually. So here's where the robot comes in. So we get a robot to actually control the tips of the instruments, to do all the moving around, and then let the surgeon sit at a little teleoperated console, a little remote console, typically still in the same room. The surgeon's still there, he's in charge. But the surgeon can comfortably sit down and operate what we call this master console, which directly controls the tips of the instruments. Robotic surgery, as I said, so it's direct manipulation, direct remote control here. You can enhance the surgery, enhance the dexterity of the instruments, and you can smooth out the motions, you can scale the motions, you can do lots of things to make this easier for the surgeon. The commercial systems that currently exist, they work great. They're very, very high performance, very precise, fairly easy to use, so I hear. But it is the first generation of this sort of technology. So they're very big, they're very expensive. There's quite a bit of overhead involved in training, maintenance, calibration, setup, etc. So these big systems have a few drawbacks. They get in the way. If you saw in the previous slide, they're really enormous, pretty much filled the room. If you look at the Da Vinci. So it's tough to integrate in a typical operating room that's already full of equipment, and you have to bring in a great big robot, and so things have to be planned out pretty carefully. And it's got to be covered up with all kinds of sterile drapes because it's a sterile environment. So our research, what we're working on, our lab, is trying to look at the existing technology, these great big robot systems, and we're saying, what if we could get a system that has the same kind of potential, the same performance, the same accuracy, just as easy to use, but make everything smaller so it doesn't get in the way. We want the thing to be able to be set up by hand. Another factor is it's autoclavable. The motors, the connectors, just about everything you see here, instead of needing the sterile draping, you can just go into the autoclave, come out again, be stored with the rest of the equipment. It doesn't take up any floor space on a regular basis. And it is a fairly simple system. It's motors, operating gears, racks and pinions, everything's right out in the open there. It's easy to clean, easy to sterilize. We have these independent, modular robot platforms. So each platform controls an endoscope or a surgical instrument, and hopefully these can all be clamped together around the abdomen and used directly. So here's the system, and it's the system you see right here. 2 instruments, 1 endoscope. So the instruments go on the manipulators go on the frame, and the frame goes on the table. And these are hopefully small enough that they're easy to position and move around and clamp into place with one hand, really. Only a few pounds each. Autoclavable and waterproof. Dump them in water, scrub them off when you're done with them, and put them in the autoclave and they're ready to go for the next time. Next. It's really just a pan and tilt like you have on a camera tripod or something like that. Miniature motors, for an endoscope you want 3 different motions: rotation, inclination, and insertion. For the instrument manipulators here, you also need to control the rotation of it. And eventually, you want to control a miniature wrist on the end of the instruments to give the surgeon some more dexterity. So when a novice volunteer operates a manual instrument, even when they're pretty careful, the manual instrument's sort of long and thin, there's going to be a little bit of manual trim. And this is what it looks like when you use a motion tracker to see what the tip of the instrument is doing. So by hand, it's a little jiggly. With the robot, there's still some high frequency vibration, because even moving a robot around on a stiff frame like this causes a little bit of vibration, and it's at a level that can actually be detected by our motion tracker. So you see the system we have. We've put together this system. It works fairly well. It's always an ongoing process. Lots of room for improvements, and it brings up a lot of interesting topics. We're engineers. If we have a fixed set of requirements that we're going to meet, we can do that. We can say, okay, it has to be this fast and this strong and this precise. We know how to do that. But when you look at something like surgery, it's not that simple. You can't just walk up to a surgeon and say, well, okay, how precise does it need to be, and how fast does it need to be, and how much force do you need, how much torque? And the answer every time is, well, it depends. Sometimes that's good enough, sometimes it's not good enough. So we have to learn a little bit about surgery ourselves. Any opportunity that we get, we talk to surgeons, meet surgeons, observe surgical procedures, see how it works, to try to meet those needs. And then when you look at the bigger picture, well, we want to make the surgeons happy, we want the patients to have good results. Hospitals want to save money, insurance companies want to save money, there's liability issues, there's patent issues. It just gets bigger and bigger and bigger. So we're looking at one little piece of the engineering part of robotic surgery and say, well, okay, can we take this technology, make it simpler, smaller, cheaper, and get it to work, just like the multi-million-dollar systems that are in operating rooms today. That's all I have for today. Any questions?